Hello everyone, welcome to my video on L'Hopital's rule. So this is another very big topic that we're going to be looking at. It combines the notions of limits and derivatives into one topic. These questions are always asked on finals, so make sure you're comfortable with this. I'm going to break down L'Hopital's rule into 4 cases. So it's going to be 4 separate videos. Each video is dealing with a specific case, and we're going to look at examples on each situation. So what L'Hopital's rule states is that suppose we have two functions f and g, which are differentiable, and the derivative of g is not equal to 0 on an open interval I containing number a, and if we have this limit over here, so the limit as x approaches a of f of x divided by g of x, and we get, this is our case 1, the indeterminate form 0 over 0 or plus minus infinity over infinity. These are the indeterminate forms that we saw at the beginning of the semester. So 0 over 0 or infinity, then what L'Hopital's rule is saying is that when we're taking the limit of f over g, then what you're doing is you're taking the limit as x approaches a of f prime of x over g prime of x. So if you're taking the limit, you're evaluating the limit, and you get an indeterminate form, 0 over 0 or infinity over infinity, plus minus, the sign doesn't matter. What this is telling us is that you're essentially just going to take the derivative of the numerator individually and the denominator individually, and then reevaluate the limit. And if you get a number, we're done. If you get the indeterminate form 0 over 0 or infinity over infinity again, well, we have to apply L'Hopital's rule again and take the derivative of the top and the bottom individually. So be very careful. A lot of students confuse this with the notion of quotient rule. This isn't a function. We're not dealing with a function with a division. So you're not applying, so this is a warning. You're not applying quotient rule on the entire thing. You're taking the derivative of the numerator on its own, and you're taking the derivative of the denominator on its own. So do not apply quotient rule, okay, on the entire thing. So we're dealing with the limits, and you're taking the derivative of the top and the bottom individually. Keep that in mind. The proof for L'Hopital's rule is very difficult, so I'm going to skip it, and we're just going to jump into examples and see how to apply this. Okay, so let's begin. So in our first example over here, it says to use L'Hopital's rule to evaluate the following limit. So the limit that's given is the limit as x tends to infinity of 3x minus 4 divided by 5x minus 2022. So let's begin. Notice that this is something that we saw at the beginning of the semester. We should be able to solve this without the use of L'Hopital's, but since we're practicing L'Hopital's, we're going to apply L'Hopital's rule here. So if we weren't going to use L'Hopital's rule, you would have just divided by the highest exponent of the denominator, right? Or factor out the highest the highest exponent on the denominator, and you could solve this problem. But let's practice using L'Hopital's rule. Okay. So what L'Hopital's rule is saying is if you have an indeterminate form, 0 over 0 or infinity over infinity, then you could take the derivative of the top and the bottom individually. So we start off by substituting the x value into our numerator. So 3 times infinity minus 4, that's infinity. And 5 times infinity minus 2022 is still infinity. So we got the indeterminate form infinity over infinity. So we could apply L'Hopital's rule. So whenever you're applying L'Hopital's rule, it's important to write the notation. You have to state that you're using L'Hopital's rule. So the way we do this is, there's different notations that you could use. Sorry. So we have 3x minus 4 over 5x minus 2022, and the notation that I use is I put an equal sign, we put a h with a hat on top. This h tells me that I'm about to apply L'Hopital's rule, and on top of it we're going to write it, which type of indeterminate form are we dealing with. So we're using L'Hopital's rule at this stage, and we have an indeterminate form infinity over infinity. Okay, so you state that you're applying L'Hopital's rule at this step, and you're using the indeterminate form infinity over infinity. So what we're going to do now is take the limit as x goes to infinity, and we're taking the derivative of the numerator. So let me write it in this notation, like maybe take the derivative with respect to x of the numerator, and we're taking the derivative with respect to x on the denominator. Okay. When we're doing this, the derivative of 3x minus 4, so we write the limit. Notice that I'm always writing the limit in the front, so don't forget to write your limits. And when you take the derivative of 3x minus 4, the answer is just 3. And when you take the derivative of 5x minus 2022, we get just 5. So we're taking the limit as x goes to infinity of 3 over 5. There's no x's in here, so the answer is just simply 3 over 5. And we're done. So this is the answer. And notice that it matches our answer, the shortcut that we saw at the beginning of the semester. We saw when we were doing horizontal asymptotes that if the highest exponents of the numerator and the denominators match, the answer is just the coefficient in front of those terms. So we expected our answer to be simply just 3 over 5. And using L'Hopital's rule, this satisfies our intuition. Okay, so let's look at harder examples and let's keep going. So in this second example over here, it says to use L'Hopital's rule to evaluate the following limit. So we have the limit as x approaches infinity of 9x plus 4x squared divided by 3x plus 25x squared. So just by looking at this, again, you should know what the answer is. But let's apply L'Hopital's rule. So first of all, we substitute x's with infinity. We get infinity plus infinity over infinity plus infinity. So this gives us the indeterminate form infinity over infinity. So let's use L'Hopital's. So we write the limit as x goes to infinity of 9x plus 4x squared over 36x plus 25x squared. Okay, so we know it's an indeterminate form infinity over infinity. We put our equal sign. We put the h with the hat on top, so this is signifying that we're applying L'Hopital's rule, and we write the indeterminate form underneath. So in this case, it's infinity over infinity. Okay, so now we're going to take the derivative of the top and the bottom, so I write my limit in the front. I'm not going to write the notation, I'm just going to take the derivative straight. So the derivative of 9x plus 4x squared is just 9 plus 8x. And on the bottom, we have 36 plus 50x. Okay. So now we reevaluate the limit, taking the limit as x goes to infinity. On the top, we get 9 plus 8 times infinity, which is infinity. On the bottom, we have 36 plus 50 times infinity, which is infinity. So once more, we have an indeterminate form, infinity over infinity. So we don't have a number, so we have to apply L'Hopital's rule once more. So you could apply L'Hopital's rule multiple times. So let's apply L'Hopital's rule again. We have the indeterminate form infinity over infinity. So we take the derivative of the top and the bottom once again, giving us limit as x tends to infinity. The derivative of 9 plus 8x is just 8, and the derivative of 36 plus 50x is just 50. Okay, and now we're taking the limit as x goes to infinity of 8 over 50. There's no x's, so the answer is just 8 over 50. They're both even, so we can reduce, divide the top and the bottom by 2. 8 divided by 2 is 4, 50 divided by 2 is 25, and that's the answer. Again, just as we expected, because we look at the highest exponent of the top and the bottom, that gives us 4, and here the coefficient is 25, so we expected our answer to be 4 over 25. Okay, so these are examples where we actually knew how to solve them without using L'Hopital's rule, but now we're going to look at different types of limits where our old tricks don't work, and we have to apply only L'Hopital's rule. So let's go ahead and take a look at that. So in this third example over here, it says to use L'Hopital's rule to evaluate the following limit. We have the limit as x tends to pi over 2 of sine x minus 1 divided by 1 minus cos of x. So I encourage you, pause the video, try to see if you could solve this on your own. Okay, so if you tried the problem and you started taking the derivative, that's wrong. Why is it wrong? Let's go ahead and evaluate. So if we evaluate the limit as x tends to pi over 2, sine of pi over 2 is 1 minus 1. And when you plug in pi over 2 over here, we have 1 minus cos of pi over 2. That's 1 minus cos of pi over 2 is 0. What you get is 1 minus 1, which is 0, over 1 minus 0, which is 1. 0 divided by 1, that's not an indeterminate form. 0 divided by a number is just 0. We're done. The limit of this, of sine x minus 1 over 1 minus cos x is just 0. You cannot apply L'Hopital's rule. Why? Because we do not have an indeterminate form. In order to apply L'Hopital's rule, this is really important, you have to have the indeterminate form 0 over 0 or infinity over infinity, plus minus, the sign doesn't matter. So only in the scenario where you have an indeterminate form can you apply L'Hopital's rule. So keep that in mind, okay? So this was a bit of a trick. So here, it's just direct substitution works. We plugged in the limit, it gave us a number, we're done. No L'Hopital's rule. Okay, so let's look at another example. Okay, so in this example over here, number 4, use L'Hopital's rule to evaluate the following limit. The limit that's given is limit as x tends to 0 of e to the x minus e to the negative x minus 2x, all that divided by x minus sine of x. Once again, pause the video, see if you could solve it. So we start off by taking the limit as x goes to 0, substituting the x's in here, we get e to the 0, which is 1, minus e to the negative 0, which is again 1 minus 2 times 0, which is minus 0, over 0 minus sine of 0, which is 0. 1 minus 1 is 0, 0 minus 0 is 0. So we get the indeterminate form 0 over 0. So since we have an indeterminate form, we could apply L'Hopital's rule. Let's go ahead and do that. So I'm going to right away go and apply L'Hopital's rule, and I'm going to write the indeterminate form that we're dealing with, which in this case now is 0 over 0. So now what we could do is take the derivative of the top and take the derivative of the bottom individually. Let's go ahead and do that. So we write the limit as x goes to 0, and right away I'm just going to take the derivative. So I'm telling my teacher that I'm applying L'Hopital's rule with my h. I told him which type of indeterminate form we have, and now we take the derivative. So the derivative of e to the x is e to the x. The derivative of negative e to the negative x is plus e to the negative x, right? Because of chain rule, the derivative of e to the negative x is just e to the negative x multiplied by the derivative of negative x, which is negative 1, and the two negatives cancel, giving us a plus, and the derivative of negative 2x is minus 2. Okay. On the bottom, we're going to take the derivative as well. Derivative of x is 1, and the derivative of sine of x is cos of x. So now we have this limit over here that we have to deal with. So let's evaluate the limit. We substitute x with 0, so e to the 0 is 1, e to the negative 0 is 1, so 1 plus 1 is 1, minus 2 is 0. So we have 0 on top, and on the bottom, if we substitute x with 0, we get 1 minus 1, which is 0. So we have another, we have to apply L'Hopital's rule once more. So we have L'Hopital's rule, and we have an indeterminate form 0 over 0 once again. So we write the limit in the front as x goes to 0, and we take the derivative of the top and the bottom individually. So the derivative of the top is e to the x. The derivative of e to the negative x is minus e to the negative x. And the derivative of negative 2 is 0, so I'm not going to write it. Over the bottom, the derivative of 1 is 0. The derivative of cos of x is negative sine. Since there's a negative in the front, it becomes positive sine of x. Okay. So we have this one here. Let's reevaluate the limit. Plugging x as 0, we get e to the 0 is 1 minus e to the 0 is 1, so 1 minus 1 is 0. And plugging in 0 into sine gives us 0. So again, we have 0 over 0. So this is the issue with L'Hopital's rule. It could actually go on forever. So we have to be careful, because there are cases where it's recursive, the function. Typically 3 to 4 let's say applications of L'Hopital's rule. You do it 3-4 times, that should be the max. You won't have questions on exams where you have to go take L'Hopital's rule 6 or 7 times. You're doing something wrong. So typically it's going to take about 3 to 4 iterations. I think that's fair for exam type questions. Okay. So we're going to take the derivative of the top and the bottom. Taking the derivative of the top gives us derivative of e to the x is e to the x. The derivative of negative e to the negative x is plus e to the negative x. And the derivative of sine is cos. Okay. Plugging in the limit, now we have e to the 0, which is 1, plus e to the negative 0, which is 1. So we get 2. Finally, we don't have an indeterminate form. We actually have a number, not 0. And then when we plug in cos of x, we replace x with 0, we get cos of 0, which is 1. And that's the answer. So it took us, what, 1, 2, 3 iterations to get the final answer. Okay. And notice that none of our other limit techniques would work here. Okay. So this is why L'Hopital's rule is very useful. So let's take a look at our final and most difficult example yet. So in this example here, it says again, use L'Hopital's rule to evaluate the following limits. We have this limit over here. So the limit as x tends to 0 from the positive side, ln of tan 2x divided by ln of sine 3x. So as I said, this is a very difficult one. So pause the video, try it on your own, see if you can get it. But let's go ahead and do it. So first we start off by replacing x with 0. And it's 0 from the positive side. So we have tan of 2 times 0. Tan of 0 is 0, but it's slightly to the right, so it's positive. And then we have ln of 0. So ln of 0 doesn't make sense. It's undefined. But since we're talking about 0 to the positive side, it's slightly bigger than 0, right? So ln of something that's slightly bigger than 0, remember your functions, let me do it in green, your ln function looks like this. So a value that's slightly bigger than 0, 0, like a bit to the right of 0, actually goes down all the way down to negative infinity. Okay, so this gives us the indeterminate form negative infinity over, same argument with here, sine of 0 is 0, but it's slightly to the right of 0, and ln of 0, or something that's very close to 0 but slightly to the right, is again negative infinity. So we have the indeterminate form negative infinity over negative infinity, or infinity over infinity. So we could apply L'Hopital's rule. So let's go ahead and do that. So I'm going to put infinity over infinity. We're going to take the derivative of the top and take the derivative of the bottom. The derivative of the top, we have to apply chain rule. So the derivative of ln of whatever's in its bracket is equal to 1 over whatever's in its bracket. So 1 over tan of 2x. And then we have to take the derivative of tan 2x. So it's important we still apply chain rule. All our derivative properties are still in applications here. So we take the derivative of tan 2x, derivative of tan is secant squared of 2x, and then the derivative of the 2x is just 2. Okay. So that was the top. Let's focus on the denominator now. Ln of sine of 3x, the derivative of ln of sine of 3x, or ln of whatever's in its bracket, is 1 over whatever's in its bracket, sine of 3x, times the derivative of sine. Sine is cos of whatever's in its bracket, in this case 3x, and then lastly the derivative of 3x is just 3. Okay. So before we apply L'Hopital's rule again, something like this, I would definitely go ahead and simplify it first before taking the next, before I reapply L'Hopital's rule. So this gives us limit as x tends to 0 from the positive side of 2 secant squared 2x over tan 2x. All that over 3 cos of 3x over sine of 3x. Okay. So another thing that I'm tempted to do, this is my personal opinion, I replace my secant and tans in terms of sine and cos. That's just the way I prefer to go about it. So I'm going to transform secant and tan in terms of sine and cos, and at the same time I'm going to multiply by the reciprocal. Because you're dividing a fraction by a fraction, this is just going to multiply and flip. Okay, so start off by transforming the secants and the tans in terms of sine and cos. So again, I'm not applying L'Hopital's rule here, I'm just changing the form. So limit as x goes to 0 from the positive side. So notice over here I'm just putting regular equal signs to say that I'm not applying L'Hopital's, I'm just simplifying. And I'm always writing my limit. So again, don't forget to write down your limit. So 2 times secant squared is just 2 over cos squared of 2x. The reciprocal of secant is cos, and then tan is sine over cos, sine of 2x over cos of 2x, and at the same time we took the reciprocal of this, we multiplied it and flipped it, so times sine of 3x over 3 cos of 3x. Okay, and at the same time I'm going to take what we have over here and again multiply it. So flip and multiply, because we're dividing fractions, so again you can multiply by the reciprocal. So this on the bottom is just the same as multiplying by cos of 2x over sine of 2x. So I took this fraction over here and then I multiplied it at the same time, not to have too many fractions. So all we're left with is this. Okay. And notice that this cos of 2x over here cancels with one of these guys here. Okay, so what we're left with is just this term over here. So we get limit as x goes to 0 plus, and we have 2 sine 3x over 3 cos 3x. Times sine of 2x times cos of 2x. Okay, let's keep simplifying. Bringing it in terms of sine and cos makes this problem actually a bit more difficult. So in this case here, it's backfiring for me. So let's use properties to simplify this. So first of all, sine over cos is tan. Sine over cos is tan. So we have 2 tan of 3x over 3. Yeah, so this is equal to tan. And here we have a property that we have to use. So the property that we're using is sine of 2 theta is equal to 2 sine theta times cos theta. Okay. Using this argument over here, we have sine of 2x times cos of 2x. That's what we have here. So that's equal to, if we divide by 2, the 2 that's here, we're going to divide it here. It's essentially taking double whatever the angles are and placing it here. So in the angles for sine and cos, we could double it and write sine of 4x. Okay, because whatever's in the angle here, you double it. So in the angles we have 2x, we're going to double it, giving us 4x, and at the same time we're going to divide by 2. Okay. So dividing by 2, I could flip this again. So this 2 is really multiplying with this 2, giving us a 4. Like, work out the details if you don't believe me. But you're essentially just multiplying by the reciprocal. We obtain 4 times tan of 3x divided by 3 sine of 4x. And now we could apply the limit. So if we replace x with 0 from the positive side, we get tan of 0, which is 0. And we get on the bottom sine of 0, which is 0. So we have 0 over 0. So again, now we could apply L'Hopital's rule. And we get the indeterminate form 0 over 0 now. So we take the derivative of the top and the bottom individually. Limit as x goes to 0. The derivative of the top is 4. Derivative of tan is secant squared of whatever's in the bracket times whatever the derivative of what's in the bracket, so times 3. All that divided by, the 3 is a constant multiple, we leave it in the front, times the derivative of sine, which is cos, whatever's in the bracket, then chain rule, multiplied by the derivative of what's in the bracket, giving us times 4. And now we could reevaluate the limit. Taking the limit as 4 times secant squared of 3x times 3. Replacing the x with 0 into secant, it's 3 times 0, and secant squared of 0 is just 1. Because secant squared, like keep in mind, secant squared is equal to 1 over cos squared. And replacing cos of 0 is just 1, so we have 1 over 1. So secant squared of 0 is just 1. So this piece here is 1, leaving us with on the top with 4 times 3, which is 12. And on the bottom, cos of 0 is 1, so we have 4 times 3, which is 12. And the answer here is 1. And we are done.